Anyway, I think others actually will join. We'll now start. I find some of them have really joined already. Okay. Very hearty welcome to the Distinguished Lecture Series 73. And it will be delivered by Professor Kiriti Chandra Sahu, who happens to be a graduate of Viishwood Burla, and we have requested him to join our INA Bhubaneswar chapter, and he has gladly accepted it. So, very hearty welcome to our Bhubaneswar chapter, Professor Sahu.
Thank you.
Professor Sahu's talk is going to be on unraveling rainfall estimation through the journey of a raindrop, a very, very interesting topic and very useful matter. Now, is the brief abstract of his topic is reads like this. I'm just reading from whatever he has sent. You might not have seen all these things. The raindrops on their descent from clouds to earth display a variety of shapes and sizes owing to intricate interactions among droplets and the atmosphere. Microphysical process such as fragmentation, coalescence, and phase change, strongly influenced by atmospheric temperature and humidity gradients, play a major role in driving the variability. The distribution of raindrops, shapes, and sizes plays a pivotal role in accurately estimating rainfall using weather radar, a crucial yet unknown aspect that currently relies on scientists making assumptions to measure precipitation. In this presentation, he will explore droplet interaction dynamics with straight and swirl airstreams. In a swirl flow, the droplet experiences opposite flow, cross flow, and co-flow conditions, resulting in distinct droplet morphologies compared to a straight airstream. His observations revealed a novel breakup phenomena termed as retracting back in swirl flow. He proposes a theoretical analysis based on the Rayleigh-Taylor instability to elucidate the droplet breakup and phenomena in swirl flows. Additionally, he will discuss some of our recent findings obtained using the inline holography techniques, which provide size distribution of satellite droplets resulting from the fragmentation of larger droplets. Shedding light on this principle, light on this intricate aspect of rainfall dynamics. He will also talk about unique raindrop research facility established at IIT Hyderabad, which is the first of its kind to replicate dynamic atmospheric conditions from the cloud to the ground. Now, so far as Professor Kiriti Sahu is concerned, he is a mechanical engineering graduate from UC Burla, passed in 2001. Then did his PhD under no other persons than the Professor Rodha Narasimham, one of the best known scientist actually that IISc Bangalore had. After that, actually, he moved for his postdoctoral to UK, and there actually he worked in chemical engineering side for postdoctoral things, and he joined as a professor in IIT Hyderabad. So Professor Sahu is a professor in Department of Chemical Engineering at IIT Hyderabad and served as head of the department from 2014 to 2017. His research interests include the study of clouds and raindrops, interfacial flows, and hydrodynamic instabilities. Professor Sahu has received several prestigious recognitions, including the Young Scientist Award from the Indian National Science Academy, INSA, New Delhi, and the National Academy of Science, India, Nasi, Prayagraj, the Young Associate and Indian Academy of Science, Bangalore, and the Basvik Award. He is a fellow of the Indian National Academy of Engineering, the Indian Academy of Science, and the Institute of Physics, UK. He serves as the Associate Editor of Industrial and Engineering Chemistry Research and is member of the editorial board of Lagumir, a very prestigious journal. Professor Sahu has served as the External Affairs Committee of the Division of Fluid Dynamics of the American Physical Society from 2024 to 2026. Now, this distinguished lecture series, as we know, it is being organized by INA Bhubaneswar chapter in association with the number of other institutions, including this university, SOA University, IIT Bhubaneswar, IMMT Bhubaneswar, NISER Bhubaneswar, and of course, ICT, IOC campus Bhubaneswar, and IEEE Bhubaneswar chapter. With all this cooperation, it is going on very well. Now, I request Professor Kiriti Sahu to please make his presentation, and it will be followed by some questions and answer. And for your information, Professor Sahu, your lectures are being recorded, and if you permit only, then actually the recorded version actually will be circulated.
Please,
okay?
Please go ahead. Thank you, sir.
Please go ahead.
Is my screen visible now, sir?
Yes, yes.
So, good evening, everybody. I'm Kirti Chandra Sahu from IIT Hyderabad. First of all, I'd like to thank Professor Acharya for inviting me to give a seminar in this distinguished lecture series, lecture 73. It's a kind of, it's an honor, actually, big honor for me to give a seminar in this forum. Today, I will talk about unraveling rainfall estimation through the journey of a raindrops. Essentially, we'll talk about the fluid dynamics of raindrops as it falls from the cloud to the ground. So before we go to the main topic, let us see where else the droplets are important. Because droplets can be found in many relevance in many engineering disciplines. Let's say starting from fluidized bed in chemical engineering, inkjet printing, the shape and size of the raindrops plays a pivotal role in the rainfall estimation. We'll talk about this more in this talk. This is a picture of bubbles, big bubbles like this of meter size rising in the mud volcanoes. And it forms a kind of dome structures and then this kind of holes. Measuring these holes and their distribution across this dome shape actually gives an idea of the intensity of the volcano. It is not only in the mud volcano, in the real volcano also, in the metallic volcanoes, it is also useful. When a dolphin moves, it forms a toroidal bubble at its wings, as you can see over here. This bubble helps it to take a turn. This is a very classical example, as you can see in the right-hand side of the slides. A droplet or end drop type of thing is a droplet falling on a liquid pool. So when you place a droplet on a liquid pool, what happens is due to the air cushion between the droplet and the surface, free surface, it's float on the surface for some time. And then due to the gravity, it actually try to drain the liquid of the drop in the drop, try to drain in the liquid pool. And by capillary action, the upward moving capillary wave forms, and that releases a secondary droplets or dotted droplet, as you can see. And this cascading process continues till the entire droplet is submerged inside the liquid pool. This is a very fast phenomena. We don't see in the naked eye. We need a high-speed camera to visualize it, but it is very interesting. This is an example where, let's say, rains are collected on lotus leaves. Due to the super hydrophobic nature of the lotus leaf, you can see that it is the rain water is not wetting the surface. This phenomena we know that it has motivated many microfluidics applications. So overall, we can say that the dynamics of the droplets are not only relevant in many engineering or engineering applications and natural phenomena, but also they are very interesting. This is a very classical topic because they are interesting and relevant. It is a classical topic. Leonardo da Vinci mentioned about the dynamic of water droplets in 1500. In Indian traditions, also rain has been talked about from the ancient time. Kautilya's Astra Shastra, which was written in 3rd century BCE, contained the record of scientific measurement of rainfall and its applications to countries' revenues and relief work. Kalidasa's Meghaduta, which is cloud messenger, which was written in 4th to 5th century CE, also talks about cloud, but in a poetic way. Now, coming to the Indian monsoon, it is a very unique event, and the Indian monsoon is highly complex because of several factors. I mean, it's a very complex process because of several factors influencing the rainfall. It is kind of most complex monsoons across the globe. As far as the accurate rainfall prediction is concerned, it's one of the grand challenge problem in the environmental research due to its relevance in understanding climate change and its accompanying socio-economic impact. Professor Carl Sasselman, who won the Nobel Prize in Physics in 2021, relates the rainfall with the global climate change. So there is a much bigger prospect to it. So this article, these pictures actually highlights asking us a question: is it too late to stop climate change? And this is a very common question which we ask ourselves also. The answer is no. In my opinion, there are two ways to handle climate change problems. First, we should measure the rainfall accurately and take preventive actions. This is short-term goal, with a long-term goal to control the climate. Now, as far as the rainfall measurement is concerned, it is far from perfect, and particularly in the Indian condition, it is very complex. Several factors such as temperature, humidity, aerosol chemistry, air current, secondary parameters such as earth topology influence the drop size distribution at different altitudes via complex microphysical processes such as coalescence, fragmentation, and phase change. In the present talk, we will only highlight the fragmentation part of it. Now, this drop size distribution is an input parameter for the Doppler weather radar that measures the rainfall. So what Doppler weather radar does it sends a signal to the cloud and get the reflectivity. Now that reflectivity is some function of the drop size distribution that relates the drop size distribution with the rainfall rate and uses a formula known as Marshall and Palomar formula, which was derived in 1948. Now, just to tell you some key aspects of this, neglecting coalescence and fragmentation, only two microphysical processes can introduce 10 to 20% of error in the rainfall measurement. And this error can be significantly high if we neglect, let's say, evaporation and air streams. Bigger raindrops are non-spherical. So essentially, when the size of the drops are bigger, particularly, let's say in the Indian condition, we must have observed that the drop size is of the order of centimeter. So the surface tension will not be able to hold the drop in the spherical shapes. and thus if you use a formula like Marshall and Palmer formula, which was derived in 1948, it was based on the spherical drop assumptions. So using a formula like this can introduce high errors in the rainfall estimation. And just to add to this, raindrop size distribution at different altitudes is largely unknown. And as I told you, this radar echoes from a raindrops is actually proportional to 6 power of diameters. And this reflectivity is connected with the rainfall rate with empirical constants A and B. And this A and B also depends on the drop size distribution, which is unknown. Now, any slight deviation also in the drop size distribution can lead to significant error in the reflectivity, and thereby it can give wrong data in the rainfall measurements. And this is typically the case, I mean, for the radar scientist. Of course, there are some satellite measurements and or direct measurements of the drop size distribution available. This left-hand side one is an example of which was initiated by the Ministry of Earth Sciences, Government of India, is known as SciPex project. So what they did is they had some kind of research flights like this with lots of electrical and mechanical sensors in it, and they take this off during the rainfall conditions, and they measured the drop size distribution and rainfall rate at different altitudes during real rain conditions. The right hand side is a picture taken from the NASA website. This gives the drop size distribution across the cloud. So here, the blue region here, the top part of the cloud, as you can see here, they are tiny droplets. The green region here indicates the intermediate size droplets, and the near the ground, you can see this red and yellow region. They are essentially the bigger droplets. So although the satellite data or the direct measurements are available, they are very limited, and we cannot get this data frequently. So researchers make assumption about the drop size distribution to measure the rainfall. Now, as far as I talk about the size of the raindrops, in light rains, when the precipitation rate is less than, let's say, 2.5 millimeter per hour, the drop size are also small, like 0.5 to 2 millimeter. This is particularly happen in kind of European conditions and so on, where they have the flat rain, there is no variation of temperature and humidity in the horizontal directions. In the case of moderate rain, when the precipitation rate is about 2.5 millimeter to 7.6 millimeter per hour, the drop sizes increases to 1 to 2.6 millimeters. In the case of heavy rain, precipitation rate when the precipitation rate is greater than 7.6 millimeter per hour, the drop size can increase to 1 millimeter to 5 millimeters. In the case of violent rain, like this cloudbursts, etc., when the precipitation rate is greater than 50 millimeter per hour, the drop size could be of the order of 1 centimeter. This is pretty big. And due to the climate change issues, we are now facing a lot of localized rainfall with high precipitation rate, where the drop size are really, really big. Now coming to the shape of the raindrops, as I told, tiny droplets which are observed in the European condition or any other parts of America and other countries, they are very small. They are of the order of 1 millimeter. So surface tension will hold them to a spherical shape. But as the size of the droplet increases, the surface tension force weakens, and that will deform the drop to a complex shape like this. But these are also simple shapes. Real raindrops are like this. This is taken in our at IIT Hyderabad, and you can see that it is about something like 7th floor, above 7th floor building or so. We can see that this is very complex. It has very tiny satellite droplets, like small droplets. This has intermediate size droplet. This has ligaments. So, and all this happen at a particular altitude. So even at a fixed altitude, the drop size can vary drastically. So, and getting this kind of information and to get the rainfall rate, we have to measure this drop size distribution very, very accurately. This is the results which I have taken. I mean, I got it from Professor G.S. Bhatt from IISc. This drop size, they have these are satellite data. they have measured the drop size distribution at a height of something like 15 to 20 kilometers above the ground level. So in a nutshell, I can tell that accurate rainfall measurements require drop size distribution in the bulk air region from the cloud to the ground. But most of the measurements are done either in the ground level or in the cloud region. In the ground level, a device known as digidometer is used. Digidometer are essentially very, very expensive equipment. These are installed in kind of aerospace, airports or in defense related areas. They have this digidometer, which and one digidometer costs about 1 crore. So they cannot install everywhere. But in there, it is measurements are done on the ground level, and all the satellite data and other measurements are done in the cloud level. So absolutely, there is no data or very limited data. Satellite data are available in the bulk air regions, and largely influenced by temperature and humidity gradient. As I told, when the raindrop falls from the cloud, the temperature is below 0 degrees centigrade and humidity is supersaturated. As they fall, the temperature increases and humidity decreases. So if you wanted to get the drop size distribution at different altitudes, one has to build a tunnel of, let's say, 10 kilometers height, which is not possible. Moreover, in Indian condition, we have the temperature and humidity gradient along the horizontal direction also. For instance, Hyderabad weather is different from the one which we get it in Bhubaneswar, or let's say Assam weather is different from Himachal Pradesh and so on. So these are kind of very significant factors in the Indian condition where we have large variability of climates as we go from one place to another. So in order to address this challenge, we have established this research facility at IIT Hyderabad. We call it Raindrop Research Facility, RRF. This has this actually recreate the dynamic weather condition from the cloud to the ground. So here what we do is rather than moving the droplet from the cloud to the ground, we suspend the drop in the test section by blowing the air in the upward direction at a terminal speed. And we condition the air in such a way that the droplet which are suspended in the test section get the local condition as if they are falling from the cloud to the ground, from high humidity, low temperature to low humidity, high temperature. So essentially we know the gradient, so we can put that and create the dynamic weather condition over here. So I'll talk more about that in the subsequent slide. So this has essentially three major units. One is the conditioning unit here, this part. It consists of cooling and humidification, dehumidification, control panel, etc. So the atmospheric air enters from here and then goes through this kind of conditioning unit, and there is a settling chamber which collects this air, and then it blows the air in a laminarized conditions, and it goes through these honeycombs, sieves, etc., which are installed over here, and with a converging section, and that goes in the test section. So there is a sonic nozzle valve here, which actually choke the flow. You can see over here, it can choke the flow. So essentially, the velocity of air, if the sonic nozzle valve is always the velocity of sound. So that actually can help us to change the airflow instantly, because the fragmentation, etc., which occurs in the test sections, the time scale is of the order of millisecond. So we have to change the flow rate instantly. And there is a vacuum pump which creates the flow. So the air enters from here and leaves from here. And the total travel time is about few seconds. And you can imagine the challenge over here, because let's say we switch on the AC to 20 degrees centigrade in a hot day. In order to get the 20 degrees centigrade temperature, it requires half an hour to reach that close to that temperature. But here the travel time itself is very, very small, is of the order of a few seconds. So inlet air will be conditioned to the desired condition all the way from the cloud to the ground. So it's very challenging. Another challenge is to suspend the drop here because of the aerodynamic force. So essentially, this has three major units: cooling unit, wind tunnel, this is a jet type wind tunnel as I have shown, and the vacuum pump. The cooling unit, which consists of primary cooling unit, secondary cooling unit, humidifier, dehumidifier, with a double feedback loop temperature controller, can vary the temperature from -10 degrees centigrade to 40 degrees centigrade of this air, which is going in the upward direction to suspend the droplet. And the relative humidity can be varied from 0 to 95%, almost from the supersaturation to the complete dry conditions, with a flow rate of 500 to 2000 meter cube per hour. You can imagine how much, and this is an open system, enters and then air enters from here and it leaves here, leaves from here. This is the wind tunnel where the droplets are suspended. There are a lot of mechanical engineering component over here, and this is designed based on the design from scratch. Actually, it is nowhere available. Then we, by maintaining the different condition over here of the blowing air, we study the dynamic of the raindrops using holography and high-speed imaging. The vacuum pump itself, which actually creates this flow, is also unique because of this, all these mechanical bands, etc. The pressure drop is very high, and we have to maintain a very high flow rate in a controlled condition. So this vacuum pump creates 400 millibar absolute or 600 millibar gauge pressure, which is it's a speed of 1,000 to 2,000 RPM. The power of this vacuum pump is 50 HP with a variable flow device which runs at 1450 RPM. Now, this is a picture when we have, the coverage we get when we established the Raindrop Research Facility at IIT Hyderabad in 2023. So as I said, the condition in the cloud is at sub-zero degrees temperature and supersaturation. Condition in the ground, for example, on a rainy day, maybe say 30 degree or 40 degree, or relative humidity can be, let's say 30%. So the droplet, when it falls from the cloud to the ground, experience the temperature gradient. The temperature increases as the droplet going down, and the relative humidity decreases all the way from supersaturation to 20 to 30 degree, 30%. So these are all challenges. And another challenge is a typical raindrops from the cloud as it falls to the ground. It takes about 20 minutes, considering that the cloud height could be, let's say, 5 kilometers or so, and the travel time could be about 20 minutes. So we have to suspend the droplets aerodynamically at least up to 20 minutes. And just to mention that we could suspend the droplet undergoing all this fragmentation, phase change, coalescence, etc. For 25 minutes using all this facility which I have discussed in the previous slide. These are challenging, and in addition to this, the inlet air, this is like blowing here in the upward directions, has to be maintained in the desired temperature and humidity conditions. So other factors which you can control in our experimental facility is aerosol content in the inlet air, and the air current, the turbulence level of the air current. Also, we can incorporate the geophysical conditions, let's say condition of Hyderabad or Assam or Bhubaneswar, in the edge. All these conditions can be incorporated, and thereby it can study the localized rainfall conditions across our country. I'll talk more about how we have done it in the subsequent slides. So these are some typical parameters for raindrops. As I said, our raindrops size can be all the way from, talking about falling raindrops, they are of the order of 1 millimeter to of the order of centimeters. So as the diameter increases, the terminal velocity also increases. These are some dimensionless numbers. So Reynolds number is essentially, this is inertia force by viscous force. For smaller droplets are about 1,000 to bigger droplet of around 8,000 or 7,000. The capillary number is essentially viscous force by surface tension force. This is of the order of 0.001. Weber number, this is a very important parameter, which is inertia force by surface tension force. This plays a vital role in the fragmentation process of the droplet. So for smaller droplet, it is about 1. For bigger droplet, it can go up to 12 or 13, 14 like that. Utop's number is essentially gravitational force by surface tension force, and that also increases as we increase the diameter of the droplet. So these are some typical parameters of raindrops which we observe in the rainfall conditions. Now, coming to the droplet interactions with the airstream. So when the droplet falls from the cloud, it can experience airstreams, and it can encounter airstream in these 3 different configurations or the combination of all 3. So this is a cross flow configuration where the droplet is falling vertically, and then there is a airstream which is hitting in the orthogonal configuration. That is called cross flow configurations. In the opposite flow configurations, where droplet is falling vertically and then there is a airstream going in the upward direction. So this is opposite flow configuration. And in the co-flow configuration, both the airstream and the droplet are falling like this and interacting with each other. So that is co-flow configuration. So now this, as I told, this is a very classical problem. Several researchers have studied this droplet fragmentation process, including some of our recent work. As I mentioned, in the cross-flow configuration, when the droplet encounters an airstream, Weber number is a parameter which characterizes the flow. Weber number is essentially, as I mentioned, inertia force by surface tension force. And I also told that the dynamics which occurs are very fast. For example, when a droplet breaks into multiple pieces, that is of the order of milliseconds. So we have to use inertia scale in order to visualize the dynamics. So when we increase the Weber number, what happens is a spherical droplet undergoes vibrational mode. Then as you increase the Weber number further, it goes through back breakup phenomena, back Stemann, multi-back, shear mode, catastrophic breakup, etc. So in a cross-flow configuration like the one droplet falling and airstream is hitting orthogonally, the critical Weber number in which this back fragmentation occurs is about 12. In a opposite flow configuration where the droplet is falling like this and airstream is hitting in the upward directions, the critical Weber number for back fragmentation is about 6. Now, this is a typical back fragmentation process, and this is a very complex process. When the droplet encounters the airstreams, you can see that here the droplets flatten out to a disc shape. Am I audible?
Yes.
Okay. So the droplet flattens out to a disc shape, and then due to the airstream, it bulges out to form a bag. This is a film and with a rim around it. And due to the aerodynamic force, the pressure difference across this tip, it ruptures over here, producing very, very tiny satellite droplets. Then what happens is the film which you see will retract towards the rim, and the rim fragmentation occurs due to the Rayleigh-Plateau capillary instability and produces intermediate size droplets. Subsequently, the nodes which are present around this rim fragments due to Rayleigh-Taylor instability, forming bigger droplets. I am telling at different stage, different mechanisms are occurring, and at different stage, different size of droplets are producing. So if you see this final stage, there are droplets which are produced due to the rupture of the film. They are tiny satellite droplets. There are intermediate size droplets which is coming from the rim fragmentations, and there are bigger droplets like this, ligaments, etc. It's coming from the node. So eventually we get a very complex size distribution, and we have to measure this to get the rainfall rate. And you can see that some of the drops in a classical 2D, I mean, imaging system, let's say pseudography or so on, you cannot get the volume information. So we have to get the volume information also. So that I will talk about in the later part of my talk. Now, when the raindrops encounters a swell airstream, let's say something is swelling, the airstream is now swelling. So in that configuration, why I choose this configuration is, in this case, the drop encounters, and this is frequently observed in the atmosphere also, the drop encounter cross flow, co-flow, and opposite flow conditions simultaneously. So this is an experimental facility. So we have a needle where we produce droplets of, let's say, different size. In this case, let's say 3 millimeters. And we have a sweller which produces the swell air streams. So in addition to, in this process, we study this kind of fragmentation of this drop undergoing this swell airflow in a swell airflow. In addition, in this kind of flow configurations, in addition to this Weber number, there is a swell number which will also influence the fragmentation process. So in this case, we have defined the swell number based on the geometry of the sweller. So this is a typical picture of the sweller. It has dome shapes here, and then there are kind of blades around it, and it has angle which it is making to the horizontal to this dome shape. So based on that, we can define the swell numbers like this. In addition to this Weber number and swell number, in this, because it is affected by a cross flow, opposite flow, and co-flow configuration simultaneously, the location at which it is interacting with the airstream also matters. So all this can influence the fragmentation process. Now, in order to study the flow field produced by this sweller, we have conducted this particle image velocimetry experiments. When the swell number is 0, essentially there is a airstream moving like this. You can clearly see that there is a region here with high velocity. This is called potential core region. And around it, there are shear regions where there is a velocity gradient. And outside there is no flow, so that is kind of wake region. In the intermediate swell, when intermediate swell strength, when there is a swell, but there are intermediate strength, you can clearly see a coronular kind of configuration over here. This wake region in the center is due to the dome shape of the sweller. This annular region, which is red region here with high velocity, is associated with the swelling kind of due to swelling. And the outside region is essentially the shear region, which is going down again. The velocity decreases as you go away from radially outwards. When the swell strength is large, however, because the mixing is now more, the shear, this high region, this high velocity regions now get mixed up, and we can have a kind of high velocity region across these entire annular regions. Follow with the low velocity in the central line regions. So this flow field will essentially influence the fragmentation process, as I will discuss in the schematic diagrams. So what happened is, for the so this is a structure. So this is a dome. So there is a wake region over here, and then there is a shear region where the swell is being dominating, and after this there is a low velocity region here. So when we have intermediate swell strength, the droplet can migrate downward directions, and it can the fragmentation process may occur in the transition zone of the shear zone and the wake zone. So now, if in this configuration, what happened is the top part of the droplet experience high velocity, whereas the bottom part of this droplet experience the low velocity. You can actually imagine this is plotted oppositely. It is kind of this. So so what happened is the top part will migrate in the upward direction, whereas the in the forward direction, whereas the bottom part will be retracting back, producing a new type of breakout mode, which we'll discuss in the next slide. When the swell strength is high, the drop will not be, because there is a lot of mixing here, and the high velocity regions are confined to this. So the droplet fragmentation also will occur in this shear zone. So essentially, it will experience kind of a flat velocity profile over here, as you can see here, and a typical fragmentation process can occur for high swell strength. So here, this is the video taken while conducting the experiment. These are two views. One is the front view, and this is the top view. two cameras are installed. So one is front view, the other one is the top view. So when the swell strength is 0, you can see that the droplet, here we kept the Weber number 11.4, which is less than the critical value. Remember, in this configuration, I told that the critical Weber number is around 12. So because the Weber number is now less than 12, the inertia force is lower than the surface tension force. So in this case, what happened, you can see that the droplet enters, and this is the potential core region of the airstream, which is coming, this is a nozzle. And you can see that the droplet, there is a competition between the surface tension and the viscous force. So it is going through kind of vibrational breakup mode. So droplet undergoes this vibration and produces this kind of droplets, the top panel of these pictures. When the swell strength is intermediate, you can see that the droplet fragmentation process occurs. I'll go back again, told you, in this region. So what happened is the bottom part of the drop here experience less velocity, whereas the top part experience the high velocity. So it gets stretched like this, You can see that the top part is going forward, whereas the bottom part is retracting relatively and forming some kind of twisting. And it creates intermediate and smaller size of drop, as you can see over here. When the swell strength is large in the bottom panel, you can see that the droplet is fragmentation process is occurring in the shear zone. You can see that the drop forms clearly a bag. Let us see one more time. And the bag bulges off, and that ruptures from the tip to produce the tiny satellite droplets. Then subsequently, the rim fragmentations occurs, as you can see over here. And then subsequently, this at later time loads also fragments to produce the bigger size droplets. So this what we see in the middle panel is a kind of a new mode which we have observed for the first time, and it was reported in our recent paper 2-3 years before. Now, coming to the theoretical modeling of this phenomena, so there are two things occurring. A spherical drop, when it is encountering the airstream, it first flattens out. Now, this drop, this shape drop, this radius increases with time. And when it becomes sufficiently thin, the aerodynamic force make it bulge to form this bag. And then after that, the length of the bag increases with time. So, so in this case, what we can do is a theory can be developed. I'll not go into detail of all this, but we can develop a theory based on the stagnation point flow for the flattened drops and investigate how this radius or diameter of this flattened drops is increasing. And by balancing the forces at the tip of the drop, we can get the length of the how the length is changing with time. So alpha is essentially the dimensionless radius of this flattened drops, and beta is essentially dimensionless length of the drop, and it is non-dimensionalized using the initial radius of the drop. So here F is the stretching factor, and this is the Weber number which we maintain of the stream of the air streams, and this is the picture which we where we plotted the temporal evaluation of this alpha, which is the dimensionless radius of this disk, and beta, which is the length of this bag. And you can these symbols over here with error bars are from experiments, and this dotted line represents the theoretical results for different swell strength. For swell number 0 is the black line, and this is 4.47, and this is 0.82. And you can see that we could our theoretical prediction is predicting the experimental behavior very well. Another thing which you can observe over here is the stretching factor F. In the no swell case, it is well known that this F, stretching factor of the droplet, is about 2√2, which is 2.82. But with the swell strength, we found that the F is increasing as we increase the swell strength. This will be used further when we get the size distribution of the droplet. Now, this is another situations which we observe in the atmosphere. Droplet falling from different heights and encountering an airstream. Now, what happened is in the previous case, what we did is the droplet was placed right over here in the potential core region of the airstream. So this is the potential core region, this is the shear zone, and this is the outer region. But what happens when the droplets fall from different heights? So when it falls from different height, essentially it has a potential energy, and that potential energy is converted into the vertical kinetic energy. So there is a competition between the vertical momentum of the drop falling from the different heights with the horizontal momentum of the airstream. So this is an experimental setup again. There is a needle which is placed at different height, and then is a airstream which is coming like this. And there are multiple cameras that have been used to study the dynamics of the drops. Now, if the drop, this is h is the height of the drop and d is the diameter of the drop. Height of the needle and diameter of the drop. H is the height of the needle and d is the diameter of the drop. And you can see that when h by d is small, so essentially when you place the drop over here, it has less vertical momentum. So it will not be able to penetrate inside. So the fragmentation process can occur only in the shear zone. But as you increase the height of the needle, what happens is the droplet gets more and more vertical momentum, and the fragmentation process can occur at different locations all the way from the top part to the bottom part. So, and even for the fixed Weber number, one can have different type of breakup phenomena. In addition to this, it is observed that when the diameter of the drop is bigger, let's say bigger means if it is more than the capillary length scale, there is a competition between the surface tension force and the viscous and inertia forces. So because of this competition, the surface tension will try to bring the drop to a spherical shape, whereas the inertia and viscosity essentially will try to, it is a dissipation, but the inertia is essentially try to deform it. So there is a competition between these two forces, and the droplet will undergo this kind of shape oscillations from the oblate shape to a prolate shape. Oblate, I mean, when the horizontal diameter of the drop is bigger than the vertical diameter. I'm sorry. And prolate drop means when a horizontal diameter is less than the vertical diameter. And A by B is essentially the aspect ratio. So when A by B is equal to 1, this is a kind of spherical drop. So here we have plotted this A by B, which is the aspect ratio versus time. And you can see that it goes through a periodic kind of shape oscillations. So a raindrop, when it falls from the cloud, before it fragments, it goes through this kind of shape oscillation. And this, because it is now periodic, the time period of this oscillation also can be obtained theoretically using this Rayleigh formula. And for fundamental mode, which is n equal to 2, we found that the shape oscillation is obtained from the experiments and numerical simulation is same as the fundamental mode of this Rayleigh frequency or time period. Now, both this height for the competition between the vertical momentum and horizontal momentum and this shape oscillation can result in different type of fragmentation process in this case. So as I said, when the h by d is small, the droplets could not enter into the potential core region, and here we just consider Weber number of around 12, which is in the critical range. And you can see that for this case, the droplet is not able to penetrate inside, and thereby the fragmentation process is occurring in the shear layer zone, and the droplet is ongoing through only kind of vibrations. So when we increase the value of h by d to 0.8, let's say, now the fragmentation process is occurring in the shear zone and the potential core region in transition between that. So you can see that the bottom part is now experiencing more velocity than the top part. So you can see a kind of retracting back breakup phenomena occurring over here. You can see in this video here, you can see this retracting back breakup phenomena. As we increase the h by d value further to, let's say, 1.9, the drop enters into the potential core region, and a typical back fragmentation occurs here. You can see that h equal to, we can see in the video, the droplet forms its back and ruptures, and the classical back fragmentation occurs. When the h by d is further high, you can see the drop fragment back and there is a stammen also. When we increase the h by d further, the drop has more vertical momentum, so the fragmentation process can occur in the bottom part of the shear zone. So again, we can see the retracting back breakup phenomena occurring there. For very high value of h by d, the droplet has sufficient vertical momentum to cross within the potential core region, and again it goes through kind of this deformations only. So these are the shape of the drop at the onset of breakers for different values of h by d. H being the height of the nozzle and d being the diameters. For low value of h by d, the droplet only forms kind of a vibrational breakups. For h by d value from 0.7 to let's say 4 to 1.1, it undergoes this retracting back. From 1.1 to 7.8, it is back, and higher values of this, it is stammen also, back stammen. When we increase the h by d value further to 7.8 to 10.6, it goes through this retracting back stammen again, and then subsequently vibrational mode again. The droplet undergoes this vibrational mode. Now, as there is a competition between the vertical momentum and the horizontal airstreams, there is an effective Weber number. The droplet, although we have a airstream Weber number, the droplet is experiencing a different Weber numbers depending on the locations. So that also can be obtained using the stagnation point flow of a flattened drops and the balancing the forces at the tip of the bag. I'm not going to detail of this. So in this case, by measuring this alpha, which is the radius of the disk once it flattens out with time, and knowing the stretching factor, which is 2√2 in this case, we can get this effective Weber numbers for different values of h by d. Why I'm showing this is this will be used to get the drop size distribution, which I'm going to talk next. Now, using this effective Weber number, when we compare the temporal variation of alpha with for different height, you can see that the theoretical predictions are in good agreement with the experimental observations. Now, what so far I talk is how the droplet can undergo fragmentation process in different kind of situation. Let's say we have slow swell flow, or you have something like falling from different height or different Weber numbers, etc. These are all classical, and most of the research till today has been ended here, like across. Whatever the research has happened around the globe. But the question is how to get the drop size distribution. This article published in Nature Physics says that a single drop fragmentation determines the size distribution of the raindrops. So essentially, we have to get the size distribution of droplets after the fragmentation process. And for example, I'm taking the picture of a object. What I will get is I will get a planar view, and most of the measurements are kind of two-dimensional pictures. That will never give us the 3D information. Of course, there are equipments like PDPA, etc., but those are for continuous flow. It will not work for droplet fragmentation. So we have used this inline holography technique and machine learning algorithms. So what it does, it uses a coherent laser light of 532 nanometers wavelength, and it hits the object. Now, when it hits the object, in this case droplet, some part of the light will refract, whereas the remaining background remains unscattered. This creates interference patterns or fringes, as you can see in this bottom figure here. These fringes, you can see these fringes around these objects, right? These fringes indicate the phase and amplitude information of the object. In this case, these tiny droplets or any object. This depth information about the object is encoded in the fringe spacings of the recorded hologram. So this picture is essentially known as holograms. Then the second step in our experiments involves the reconstruction of volume to get the 3D shape and position of the droplet. This has a lot of mathematical equations, but I have eliminated that, essentially Rayleigh Sommerfeld equations, etc. If anyone is interested, can follow our papers over here. And the last step is to use a CNN-based machine learning algorithm for the sedimentation, essentially to find out the boundary. So what it does is, let's say I'm taking the picture of mine. It creates interference patterns around me. And by considering different slices, let's say when I'm close to my face, I get this nose, tip of the nose, and I take the slice in the depth directions, and I can get the different boundaries. When we collect enter all these boundaries, we can get the shape of the object. So this is the philosophy behind this inline holography. So you can see in this hologram also, this video, you can see that as we go in this depth, at some point the size of the drops, the drops are completely visible, but as we go away, it is becoming smaller and smaller, and then finally it is out of focus. So by collecting all these informations from here, we can get the volume information. So this is a demonstration. In the typical pseudography, this is the droplet, it encounters an airstream from the bag, and this ruptures fragmentation process. In this image, you cannot get the volume information because some drops are out of focus, some drops are in focus, and because it is in the 3D space. But when we use holography, we have, these are recorded holograms, and then we can pre-process the holograms to different depth, as I told you here. So for example, if we zoom this picture, you can see some part of the drop, but when we go to the another depth, we can clearly see this droplets. So by collecting this information in the depth directions, we get the how many drops of different size are present in this control volume. Then we propose a theoretical model. This volume probability is essentially the ratio of volume of the drops of a specific diameter to the total volume of the droplets. And here we use gamma distributions and log normal distributions, which are frequently used in spray community. These histograms are coming from the experiments, and these lines are from the theoretical theory. And these contributions coming from back fragmentation, ring fragmentation, node fragmentations are highlighted in the blue color, and the overall contributions are in the black line. You can see that both log normal and gamma is predicting the experimental behavior pretty well, but the gamma is better because it also predicts the smaller size droplets, which are this is like volume probability versus the normalized diameter of different size of drops. You can see that these are tiny droplets. So it is also predicting the tiny droplets very well. In addition to this, this also can explain the mechanism of different fragmentation process. So for this droplet fragmentation, one can use gamma distributions. So here we have presented the effect of Weber number. So as I said, when the Weber number is greater than 12, the droplet is going through this kind of fragmentation process. So when the tip of the bag ruptures as the time progresses, it produces tiny droplets of, let's say, 100 micrometers. And this n represents how many of this kind of droplet of this size are present in this histogram. So subsequently, the rim fragmentation occurs and produces the intermediate size droplets. Finally, the nodes produces bigger droplets, which are, let's say, 500 micrometers or so on. In this case, so when we plotted this overall drop size distribution, we can see here. Now the bag produces tiny droplets, the rim produces intermediate size droplets, and the node produces bigger droplets. Here you can see this d by d naught varying from 0 to 1. You can clearly see there are 3 distinct peaks. So it is a trimodal distribution. Now when the Weber number is very high, first the bag forms ruptures to produce tiny droplets. So when this first bag ruptures, there is a second bag formation, and subsequently the second bag also ruptures, producing more tiny droplets. So it produces more tiny satellite droplets, and then finally the node fragmentation and the rim fragmentation occurs, and produces bigger size droplets. So it will produce only two characteristic size. As you can see in this plot, this is volume probability versus d by d naught. You can see there are two characteristics peak only. So it is bimodal size distribution. Okay. So similarly, when we study the effect of swell number, for intermediate swell number, there are two distinct peak over here. So it is bimodal size distribution. In the back fragmentation, there are three characteristic size over here. So they are multimodal fragmentation. Here we have plotted the mean diameter, normalized mean diameters of a specific size of droplet with the bigger, the primary droplet versus time. As you can see, as you can increase when we increase the swell strength, the number of the satellite drops are smaller in size after fragmentation. These are effect of height again. I'll not go into detail because this is repetition. For h by d equal to 0.8, you see a retracting back breakup phenomena and bimodal distributions. And this is back fragmentations for h by d equal to 1.9. So there are three characteristic size trimodal distributions. For higher value of h by d, again we get back Stemann breakup. So it also has clearly three characteristic size. So trimodal size distribution. So now in the second part of this talk, we observe this drop size distribution after fragmentation. But what we'll do with the drop size distribution? So this comes to the final part of my talk, how this drop size distribution is related with the rainfall. You must have observed that when the droplet, when the rain occurs, there is kind of updrift. This air goes in the upward direction. That is called updrift, and that is due to the temperature gradient from the ground to the cloud. So this is warmer and this is cold. So there is a updrift in this vertical direction. So the droplet falling, but then it encounters airstream in the vertical direction. And the typical Weber number in this configuration, as I said, are about 10 to 20. So, or also smaller. From 0 to 20, I can say. For Weber number about 9.38, because this is now in this configuration, the critical Weber number is 6, as you know. The back fragmentation occurs at critical Weber number of 6. So because the Weber number is 9.38 here, the inertia force is more dominant than the surface tension force here, and the rain drop undergoes this back fragmentation process. When Weber number is about 16.9, it undergoes back Stemann breakup. For high Weber numbers, it goes through these dual back fragmentations, like the classical one which we have seen in the previous slides. Now, comparing to with the previous rainfall models. In the previous rainfall model, the key limitations, like the one which I showed in the Nature Physics papers by Ballurmox and Bosa, that model, or any other previous model, does not adequately estimate the rainfall under varying atmospheric conditions. Moreover, the average diameter of the droplets in their model, which is essential for rainfall prediction, is a priori unknown, and there is an input parameter in that model. So essentially, they assume the average diameters. How do you know if you don't measure the average diameter? So essentially, they have the fitting parameters in their model. But our model does not require that, because we get the drop size distribution from the holography. And here we have plotted the number size distribution versus normalized diameters of the raindrops. The black line here is the previous results. This one. This blue line is Marshall and Palmer formula, which is here, and the red line from the present theoretical model and the present experiments. And you can see that our experimental and theoretical model predict the Marshall and Palmer behaviors very well. And Marshall Palmer essentially did the direct measurement in a steady rain conditions, and our experiments predict their behavior pretty well. Whereas Ballurmox and Bosa's theory does not predict the behavior, particularly for bigger sized raindrops, which are observed in Indian conditions. Now, comparing our results with the in situ measurement, remember in the very first slides, in the early slides, I talk about the measurement done by the SciFax project by Government of India, Ministry of Earth Sciences. They have essentially research flight equipped with all the sensors, and they measure the rainfall rate and the drop size distribution in 2011, October 19, October 20, and these October 19 experiments were conducted in Bhubaneswar. In 20, it is Bhubaneswar to Vijayawada flight, and October 27, it is Vijayawada to Hyderabad flight. And these are done at different altitudes. Edge here are altitude. You can see that 7 kilometers height, 6 kilometers height, and so on. So their results and the experiments which we have conducted in our laboratories, and this, by the way, these experiments which are conducted in SciFax projects are like multi-hundred crore projects. These are, but our experiments are free. So here we have plotted this volume probability versus normalized drop size distribution, and you can see that our experiments predict the real in situ aerial in situ measurements obtained from the SciFax project pretty well. I must thank here the Indian Institute of Topological Meteorology, Pune, for helping me to get this data obtained from the SciFax projects. Now, okay, we got the different drop size distribution. So how it is related with the rainfall? So let's say we know how many droplets of different size are present in a particular control volume. So we know n, how many droplets of different size are present. So we can integrate, and we know the terminal velocity of each of these drops. So pi dq by 6 is essentially the volume. Multiply with the n is the total volume. When you multiply with the u and then take a integrated with the diameters, it will give you the rainfall rate. And with a little bit of simplifications obtained from these gamma distributions, etc., we can write the rainfall rate formulas as this one. This is our rainfall rate model for weather radars, particularly in the Bhubaneswar, Vijayawada, and that conditions. And you can see that this is the inverse of the average diameters which we obtain from our experiments is related with the rainfall rate, millimeter per hour. And this formula is very much in agreement with the Marshall and Palmer formulas, because that was in the light rain conditions. So by conducting such experiments in different part of our country, we can get this region specific rainfall model. That is our objective actually. So the take home message from my talk is the studies of clouds and raindrops are very relevant, and not only relevant, but they are also interesting. And this is the article which Professor Narasimha gave me long before when he was around. It says that physicist, your planet needs you. I just wanted to conclude saying that this is just the beginning of our research and far away to go, because you have to get the region specific model of different part of our countries so that we can get the better estimations of the rainfall. So with this, I'd like to acknowledge my students, postdocs, collaborators, former students, and all the funding agency who have supported me in my research. And finally, I'd like to thank you for listening to me and inviting. I particularly thank Professor Acharya for inviting me to give a seminar in this distinguished audience, for the distinguished audience. Thank you very much for your kind attention.
Thank you very much, Professor Kiriti Sahu, for your excellent lecture. So I was just thinking that as if actually the rainfall is taking place and I'm standing here.
Thank you. It is a compliment.
Anyway, so now actually this whole thing is open for discussion. So we have actually many prominent people here present. Possibly they will have certain doubts and relevant questions. So, Professor Dikitilu, are you present? Professor Dikitilu? He was present. Somehow actually he has left.
Yeah.
So, and anybody else actually, please come up. Professor P.K. Misra, Professor Kulomani Parida. Anyway.
May I
So
ask sir
you-
one question?
Yeah.
Please do ask.
Sir, like when we talk about predicting technical point of view, if you look at when we go for the remote sensing, how effective do the radar reflectivity rate, that is Z to R, relations usually capture the journey of raindrop, and what limitations arises due to the drop deformation and turbulence while it is coming from
Yeah. So
sky? Yes.
this is a very good questions, and essentially that is the motivation of our research which we are conducting. So what weather radar does, it sends a signal and get the reflectivity. Now the reflectivity, it's essentially a light going to the cloud and returning back. So cloud
Right.
has, or the region where it is focused, essentially has kind of drop size distribution, and that drop size distribution is essentially the reflectivity. Now that reflectivity of the radar is proportional to the sixth power of the diameter of the
Okay.
droplet present,
Okay.
and you do not know the drop size distribution over there. So
Right.
and currently that is an assumption for weather radar scientists across the globe. Nobody knows. So because of course there are some satellite data or measurements available, but they are very limited. Every time you cannot have a satellite data or measurements. So as you can see, the Indian government experiments were conducted in 2011 and another one conducted in 2015.
15, right?
So this HyperX project. So you cannot conduct this kind of experiments every time because it is expensive.
It is very, very expensive,
Uh-huh.
right?
So whereas our experiments which you conduct in the laboratories, we have shown that it is predicting the behavior of what is observed in the in situ measurement by a SciPex project in Bhubaneswar, Vijayawada, and Hyderabad. That gives a lot of confidence in our research. Initially, when I started, trust me, around 2013, and all due to actually Professor Rodon Narasimha. Sir, I just wanted to correct, I'm not a direct student of Professor Narasimha. I was a student of Professor Ramagovind Rajan, and
Okay.
Professor Narasimha was there. So, so what happened was, in 2013, he one day called me in the Deepavali day, and he said that me and many scientists here in India are working on cloud, but nobody is working on the falling raindrop. Why don't you work? But he wanted me to do numerical simulations. Because I was a numerical simulation person in the training, as far as my training goes. I have never done experiment in my life before I started. I did some experiment, and then subsequently what happened is I thought that this is not answering a big question. So I met him again in 2017 with a set of question, and I thought that this is my idea. Then he said that, go, I mean, this is what I wanted to do, but because you're a numerical guy, I did not advise you. Then I went ahead. It took me 12 or 13 years to establish this facility, madam.
Yes.
But and with a lot of kind of fear that whether it will work or not, I did not know a priori. So, but I am very happy that it could get some data which is comparable with the SciPex projects. Now we have to get the region specific model because our country has different climatic zone. You cannot wait a radar, even if you get the reflectivity, how you will use it is only using Marshall and Palmer. So if I am using a formula which is in Hyderabad, same formula I cannot use in Himachal Pradesh where there is a cloud burst. So I should use a different formula. So the whole idea is to get the region specific model for our country. European and other part, they don't face this problem because they have the uniform flat land, and weather in Italy may be similar to France. So, but we face this problem. Hyderabad, across this thing, from here to 50 kilometers, we get different weather. So we have a lot of variability in our condition. That is very challenging.
Okay, sir. Thank you, sir. Thank you so much, sir.
Thank you very much for asking this.
Any other question? Okay. So now may I request Professor Renu Sharma to please propose a vote of thanks for this excellent lecture. And if we can really find out, region-specific model, and in particularly in those areas which are affected by heavy rainfall or flash flood, I think that is actually will be very, very important. Professor Sharma, please.
Thank you, sir. Thank you so much. A very good evening to one and all present in this distinguished lecture series. On behalf of Indian National Academy of Engineering Bhubaneswar chapter, I am thankful to Honorable Damodar Acharya sir for organizing such a wonderful event where we could able to get Professor Kirti Chandra Sahu. I expressed my heartfelt gratitude to eminent speaker today. He is from the Department of Chemical Engineering, IIT Hyderabad. Thank you, sir, for delivering an enlightening and thought-provoking lecture on a very crucial topic, this unwilling rainfall estimation to the journey of a raindrop. Usually we predict through the rainfall. You predict things with a raindrop. Your scholarly insight and lucid presentation really enrich my understanding and the people, those who are listening and will be listening through this recorded video. I sincerely thank all the partnering institute, SOA University, CSIR, IMMT Bhubaneswar, IIT Bhubaneswar, NISER Bhubaneswar, ICT, IOC Bhubaneswar campus, IEEE Bhubaneswar section for their valuable collaborations and support. I also appreciate the enthusiastic participation of all the faculty members, research scholars, students, attendees, and fellow INE, esteemed fellow INE members, those who are attending this. Last but not the least, again to the Damodar sir for giving us an opportunity to listen such wonderful lecture. Thank you all. Thank you so much. Namaste, sir.
I must thank you
so much.
and Professor Acharya sir for inviting me for this event. Thank you very much, sir.
Professor Kirti, whenever you are visiting Odisha, please do visit Bhubaneswar, and possibly actually we can do something better.
Yes,
Okay.
sir. Thank you, sir. Thank you very much,
Thank
sir.
you so much.
Namaste, sir.
Okay.
Shall I quit, sir? From this?
Please. Thank you so much.
Thank you very much, sir.